Okay, so let's do this worksheet to go over some of the ideas of continuity. All right, use the graph to determine the limits and discuss the continuity of the function. Okay, so the limit as x approaches 2 from the right, come down here, and we seem to approach 3. Limit as x approaches 2 from the left, come up here, and it seems to be 3. So both right and left hand limits exist. They're equal. So I get that the limit as x approaches 2 is 3. But is x continuous at 2? No, not continuous at 2. Because notice that f of 2 is 4. And so the limit as x approaches 2 of f of x, which we found to be 3, is not equal to 4, which is actually what f of 2 is. Hence, it is not continuous at 2. The limit existed, but it wasn't continuous. By the way, this is a removable discontinuity because the limit did exist. All right. So let's go to some functions and see if we can decide whether there are any discontinuities, and then classify them. Okay, so 2x plus 3 sine x. Well, 2x is just a polynomial. It's continuous everywhere. 3 sine x, that's just one of our functions that's continuous everywhere it's defined, and it's defined everywhere. So this is two continuous functions being added together. This is continuous everywhere on the real line. Okay. Here we have a rational function, so we know it's not going to be continuous where it's not defined. So I'll have to figure out the factoring here. So factor the denominator, that would be x plus 2, x minus 5. Okay. So we know there are some discontinuities. Definitely -2 and 5 because it's not defined there, and that's the only place where rational function will have discontinuities, where it's not defined. But there's a difference, remember? -2 is coming from this totally canceling factor. That's going to be a whole, and that's going to be removable. Whereas 5 is coming from a 0 in the denominator that's not 0 in the numerator. That's a vertical asymptote, and that is non-removable. Okay. Now let's see about this function. Let's see if we can find any discontinuities. Well, individually, this is a line and another line. So individually, these are fine. So the problem, the only potential problem, is at x equals 2, where these are supposed to meet up. So that's what we'd have to figure out. So in order to do that, let's go through our conditions. What is f of 2? All right, well, 2 is in here. So 2 goes in, I get 1/2 of 2 plus 1. So that's 1 plus 1. So f of 2 is 2. All right, now let's take the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. Okay, from the left would be less than 2, so we're in this piece up here. So I do the limit as x approaches 2 from the left of 1/2 x plus 1. But that I could just plug in 2, and I get, well, what I had above, 1/2 2 plus 1, I get 2. From the right, though, I'm down here. So limit as x approaches 2 from the right of 3 minus x. Plug it in, 3 minus 2 is 1. Okay, well, both left and right limits exist, but they are not equal. Okay, So what we see is the limit as x approaches 2 of f of x does not exist. Okay, so therefore we have a discontinuity at x equals 2. And because the limit didn't exist, it's a non-removable discontinuity at x equals 2. All right, in fact, it's some sort of jump. Okay. All right, we have a very similar problem here, but the one we did before, we have to find the value that'll make it continuous. So we're going to try and find a and see if we can force it to be continuous. So this is perfectly continuous as long as it's defined. So we'd have a problem of 0, but it's not even addressing 0 there. In the second piece, it's going to be continuous in itself because it's a polynomial. So the issue is what's happening at x equals 0. All right, let's go through our steps again. Let's find what f of 0 is. Well, it's in here. So it's 3a minus 2 times 0. So it comes out to be 3a. All right, the limit as x approaches 0 from the left would be when it's less than. So that's going to be 4 sine x over x. That's our special limit, okay? This piece here is the special limit, so we have 4 times the limit as x approaches 0 of sine x over x, that's 1, so we get 4. The limit as x approaches 0 from the right of this function, well, to the right of it, it looks like 3a minus 2x. And that would be 3a minus 0, or 3a. Now, we're trying to ensure that it is continuous, so we need these two to match so that we get continuity. I'm sorry, so that we get the limit. And then, because it's going to be equal to 3a, and there's 3a, it will all work out to be continuous. So, I need 3a equals 4. In other words, I need a equals 4/3. That will ensure that that entire function, that function is continuous on the entire real number line. Okay, IVT. Verify that IVT applies to the indicated interval and find that the value of C. So we're going to find the value where we get the prescribed value of the function. We're going to find the value of x where we get the prescribed value of y. All right, so the first thing is here we just have a polynomial. And so f of x is continuous on 0, 5. Remember, we need that for IVT. Okay, so we have the necessary condition. All right, so then I find what f of 0 is. 0 plus 0 minus 1. So it's negative 1 there. And f of 5 is 25 plus 5 minus 1, so 29. Okay, so now we're not doing the bisection here. We're being asked to find k of 11, right? So the real important thing is that negative 1 is less than 11, which is less than 29. So our k happens to fall between f of 0 and f of 5. So that says that there must be a c where this takes place. So there must be a c in 0, 5 where f of c is 11. So now normally that's about all that our theorem can do. Because this is manageable enough, I can actually figure out what that value is. But that's not what the theorem does. The theorem just says it exists. All right. So what we're saying is f of x being x squared plus x minus 1, we want equal to 11. So x squared plus x minus 12 is 0, bringing over the 11. X, okay, 3 and 4. X minus 3, x plus 4 is 0. So solving this gives me x equals 3 and x equals negative 4. So at 3 and negative 4, this function takes the value 11. But the IVT was only referring to one of these because we were guaranteeing the interval 0, 5. So that means 3. So c equals 3 is the specific value that IVT was referring to here. It said there is at least one number in that interval where the function takes that value. In this case, it was 3. Okay.